The ability to represent an algebraic function as a straight line allows mathematicians, scientists, and social scientists to model real-world behavior and make predictions. All of this would not be possible except for the work of René Descartes. René Descartes, who we've mentioned, as I said many times, and we will mention again, was a French mathematician. In 1637, Descartes published a book called Geometry, in which he created a method for producing a geometric picture of an algebraic equation. In effect, Descartes had invented graph paper by constructing two number lines which intersect at right angles at 0 on each line. Graph paper represents what is called the Cartesian plane, an adjective form of Descartes' name. The adjective, Cartesian, means we are using graph paper and on a plane. A number of 17th century scholars, most of whom were French, contributed to the development of the graphing of equations. And we'll see later on that the graphing of equations led to the creation of calculus. We'll start with some simple equations. We'll look at them in terms of what the basic structure of a linear equation is. We'll look at some graphs. We'll look at some problems where we'll use the graphs and the equations of those graphs to solve problems, answer questions, all of which are equations that can be displayed as a straight line, linear equations. Thus, the name of this lecture, the linear function. Begin with equation y equals 2x plus 4. And what we have two variables. Y is the output variable, x is the input variable. And we want to create is a roster of points that we have numerical values for x, which are substituted for x in the equation, and the value we get out is the y. The roster that you see is simply the value, some values of x and y. I've selected values of x, integer values of x, from -3 to +3. And the y values are obtained by replacing the x in the equation, y equals 2x plus 4, with that particular number. So we replace x with -3. 2 times -3 is -6, plus 4 gives us the y value of -2. There are two important ordered pairs that can be noted. Notice that when x is -2, y is 0. And remember, 0 is a very important number, and we'll see graphically it has a name. And when x is 0, y is 4. So we have two values, two ordered pairs that contain 0. An extremely important pattern can be observed if we move down the roster. Every time x increases by 1, y increases by 2. It happens for every value of x. Notice we go from -2 to -1. In the x column, y goes from 0 to 2. Change of 1, an increase of 1 in x, y increases by 2. We go from 0 in the x to 1 in the x, and y goes from 4 to 6, an increase of 2. If we increase x by 2, say from -2 to 0, y increases by 4, twice 2. And if we increase x by 5, then y increases by 10, 5 times 2. If we try another equation, y equals 5x minus 10, we notice that when x is 2, y is 0. Again, we have a roster of points. The values of x are the same, -3 to +3. The values of y are obtained by replacing x with each of those numbers and getting the y value out. For example, if we put in -2 for x, 5 times -2 is -10, minus 10 is -20. Now, when x is 2 in our roster, we'll notice that y is 0. And we, of course, also see that when x is 0, y is -10. And we'll notice further in this roster that as x increases by 1, y increases by 5. So when x goes from -1 to 0, y goes from -15 to -10, an increase of 5. Each step, when x increases by 1, y increases by 5. Okay? Let's take a look at a third equation. Y equals negative 3x minus 6. Notice now we have two negative numbers, the negative 3 and the negative 6. Our roster still contains values of x from negative 3 to positive 3, and the values of y are obtained by replacing x with each of those values of x. Now, let's notice again, we have a place where y is 0. When x is negative 2, y is 0. When x is 0, y is negative 6. And notice, as we increase x by 1, y decreases by 3. So as we go from negative 2 to negative 1 in the x column, an increase of 1, y goes from 0 to negative 3, a decrease of 3. As we go from x of 2 to x of 3, y again decreases by 3, from negative 12 to negative 15. The value of x that causes y to be 0 is called the x-intercept. And there is no special mathematical symbol for the x-intercept. If you write the general equation for a linear function, Descartes, in fact, was the first person to use the term function to describe an equation. And we write that as y equals mx plus b. We'll find out that this m and this b have really important meaning. We can see that if x, we want to solve for x when y is 0, we will get that the value of x that makes y 0 is negative b divided by m. So that is, in fact, the x-intercept. For any equation of the form y equals mx plus b, the x-intercept will be negative b over m. So if y equals 2x plus 4, that was the first equation we looked at, the x-intercept should be negative 2. And indeed, when x was negative 2, y was 0. In y equals 5x minus 10, the x-intercept should be a 2. That is 10 divided by 5, and indeed it was. And in y equals negative 3x minus 6, the x-intercept should be at negative 2, and it was. The value of y when x is 0 is called the y-intercept. The lowercase letter b, y equals mx plus b, is the universal symbol in algebra for the y-intercept. It's very simple to see when you look at y equals mx plus b, yb must be the y-intercept. Because when x is 0, no matter how big m is, anything times 0 is 0, plus b is b. So when x is 0, y will be b. Looking at our three equations, when y is 2x plus 4, the y-intercept should be 4, and it was. When we had y equals 5x minus 10, the y-intercept should be negative 10, and it was. And in the third equation, y equals negative 3x minus 6, the y-intercept should be negative 6, and it was. So once again, algebra works. Okay. The amount y changes when x increases by 1 is called the slope. S-L-O-P-E, the slope. And the symbol for the slope is m. There are varying stories as to where the m came from. In fact, I tell my classes, it originally was called mlope, but people couldn't pronounce mlope. They made it slope, but they left the m from mlope. That's, of course, a fairy tale. In reality, the stories all indicate the same thing, that it was the first letter of a word either in French or in Latin that talked about the change. And therefore, since most of the mathematicians who worked on linear equations back in the 1600s were of French descent and therefore spoke French, and since the scholarly writings were written in Latin, this makes a great deal of sense. But whatever the reason for it, m is the slope in algebra. Examination of the three equations previously revealed that the number in front of the x was the amount that y changed when x increased by 1. In general, the slope can be found, m is equal to the change in y over the change in x. All we have to do is find 2 points on the line, or 2 points in the roster, or 2 points in the equation, and subtract the y, subtract the x's, divide those changes, and we'll get the slope. We can now return to our roster of ordered pairs for which y equals 2x plus 4 and graph the points in the Cartesian plane. Graph it on graph paper. Okay? And the points are simply those places that correspond to the ordered pairs in the roster. So that, for example, we can see that we have points at -3, -2, at -2, 0, at -1, 2, at 0, 4, at 1, 6, at 2, 8, and at 3, 10. This corresponds to the 7 ordered pairs in the original roster. We also notice that these points all line up. And since they all line up, we can draw a line through the points. Now, the fact that this kind of equation, y equals mx plus b, is graphed in the Cartesian plane as a line is why we call these linear equations. The slope remains a constant. There is no change, and therefore, since there's no change in the slope, the graph is a line. Now, the graph itself indicates not just these 7 points satisfy the equation, but any point on the line, even points where the coordinates are fractions, even a point where the coordinates are irrational. But for any real number coordinates on that line, those x and y values will work in the equation. And any point that is not on the line will not work in the equation. That's kind of nice to know. So there's an infinite number of points that work, and there's an infinite number of points that do not work. Okay? And again, the rationale for calling these linear equations is that if you have an equation, y equals mx plus b, its graph on the Cartesian plane will always be a straight line. If you plot the points and they don't line up, either you've misplotted or your arithmetic for the roster was incorrect. There are 2 special kinds of linear equations that involve the use of only one variable. The first is y equals k, where the letter k stands for a constant. For example, y equals 2 or y equals negative 4.7. In all cases of y equals k, the line is horizontal. The slope is 0 because there's no x. You can write it as y equals 0x plus k. So the slope is 0. There's no change in y as x goes from left to right. We have a horizontal line. If we have an equation of the form x equals k, x equals a constant, x equals 4, x equals negative 2, etc., we have a vertical line. And now we talk about having either absolutely no slope or an infinite slope or a undefined slope, because indeed there is no change in x. X is always whatever k is, and the line is vertical. We can use lines and linear equations to solve and examine real-world situations. We'll first investigate a postage model. Let us assume that one must pay 50 cents for the first ounce on standard postage and 25 cents for each additional ounce or fraction thereof. You may say, wait a second, this is a little more expensive. Well, we're looking to the future. We know the price of stamps is not going to go down. And so therefore, at some point in the future, we'll be paying 50 cents for the first ounce and 25 cents for each additional ounce. We know that every time we add an ounce, 1 ounce added, we get 25 cents more in cost. So therefore, we know that the slope must be 25. We also know that if we have no additional ounces, if our mail or envelope weighs less than, or it weighs 1 ounce or less, I should say, our price is going to be 50 cents. So 50 cents is going to be the y-intercept because x represents the number of additional ounces. And we now have the equation y equals 25x plus 50. Okay? Now, see what that means. We have a slope of 25, which means every time I add an ounce or a fraction of an ounce to my envelope, I pay an additional 25 cents. And a y-intercept of 50, which means that if I have no additional ounce, if x is 0, I will pay 50 cents. This model can be used to find the postage for a 10-ounce package. Since 10 is the number of ounces, and it's 9 more than the first ounce, our x is 9. And if x is 9, then y is going to be 275. 275 cents is $2.75. So a 10-ounce envelope will cost us, in this system, $2.75. The model can also be used to find how much something weighed if the postage required to mail it was $4. And in that case, we would have an equation. We have the equation y equals 25x plus 50. And we know that y is 400. 400 equals 25x plus 50. Now, solve for the x. Well, it turns out x is 14. That means that we had 14 additional ounces after the first ounce, and that our package weighed 15 ounces, and that's why it cost $4. So we, again, most people do not walk into a post office with an equation notes in their hand or a graphing calculator and say, let's figure out how much this is going to cost. In fact, since post offices take credit cards, most people just walk in, whatever it costs, they pay, and that's fine. But the fact is, we can examine a simple model like the postage model that enables us to understand how we can do much more complex things. And that's what we're about to do, because we're going to examine a revenue and expense model. Revenue, of course, is the money that a company or a person takes in every time they sell a unit of product or service. And expense is the cost, both the cost of generally doing business plus the additional cost for creating and selling each additional unit of product or service. Okay. So if, for example, we had a product that sold for $100, the revenue model would be Y, which is the total revenue, equals 100X. X being the number of units of product or service that we sold. Okay, so Y equals 100X. The slope is 100 since selling one more item or one more unit of service gives us $100 additional revenue. The slope is the change in the revenue for each additional unit sold. The y-intercept is 0 because if we sell nothing, we take in nothing. So therefore, you can write the equation you want, y equals 100x plus 0, but we simplify it, y equals 100x. If the direct cost to produce and sell each item is $50, that is, to produce and sell a unit of whatever you're selling costs $50, and the fixed cost or overhead is $1,000, which means no matter if you sell nothing, it still costs you $1,000 to have the business involved, then the expense model would be y equals 500x, y equals 50x plus 1,000. 50 being the slope, 1,000 being the y-intercept. If we sell nothing, we still have expense of 1,000. For each additional unit we sell, we have an additional $50 in costs, in expense. If we graph these two equations, we find that they intersect at x equals 20 and y equals 2,000. This intersection point is quite significant since it is called the break-even point. If we sell exactly 20 units, we neither make a profit nor take a loss. If we sell fewer than 20 items, we are losing money. The revenue line, the line representing the revenue equation, is below the expense line. Therefore, our revenue is less than our expenses and we're taking a loss. If we sell more than 20 units, the revenue line is above the expense line and we're making a profit. The amount of profit or loss can be determined from the model if you know how much you sold. Okay? The number of items sold to generate a specific amount of profit can be determined. It should be noted that we can solve for the break-even point. All we've got to do is set the two equations equal to each other. That is 100x equals 50x plus 1,000. Using algebra, we can solve and we get 50x equals 1,000, x equals 20. So we could solve that break-even point graphically, or we can do it with algebraic methods. Either way, we get the same answer. It's always nice to know that you get the same answer. And basically, the break-even point for business is a very, very important location because if you don't reach it, you're not making a profit, and after a while, you're out of business. We can also use linear models to compare various cell telephone plans. And as you know, in today's world, you go out there and everybody has, it seems like an infinite number of possible plans. And you want to know which plan is best for you. So we're going to look at 4 specific plans. One costs you $20 a month with unlimited free minutes. That's it. You don't pay any additional minutes, but you got to pay the $20 whether you use any time or not. You can have a 2 per minute charge with no monthly charge. So if you don't use anything, you pay nothing, and each minute you use, it costs you $2. A third plan would be a $1.50 per minute and $5 monthly charge. So basically you have no usage, you still cost you $5. And the last plan is $1 per minute with $10 in monthly charges. You can write each of these plans as a linear equation, and we have. We have y equals 20, which is the first plan, $20, no matter all the minutes you want to use. The second plan is y equals 2x, because we have $2 per minute. That's the slope. Each additional minute costs you $2. The y-intercept is 0. If you use no phone calls, it costs you nothing for the month. The third plan is y equals 1.50x plus 5, $1.50 per minute and $5 monthly charge. And the final plan is y equals x plus 10. 1x plus 10, if you like, that is $1 per minute and $10 for the monthly charge. We can graph these four equations, and by looking at the graph, examine which is the best plan. So let's go to the Texas Instrument TI-83 and see what these graphs tell us about these plans. Here we have the four graphs displayed on one Cartesian plane. Each line represents a different plan. The horizontal line is y equals 20. That is $20 per month, unlimited number of calls. The line above it is y equals x plus 10, or 1x plus 10, and that is the line for the plan where you pay $1 per minute and you pay $10 monthly charge. The next line would be y equals 1.5, actually 1.50x plus 5. The calculator drops to 0. And that would be the plan, $1.50 per call, per minute of call, and $5 per month. And the line on top, at least where the little cursor is flashing, is y equals 2x, $2 per minute with no monthly charge. You'll notice, the first thing you should notice is all four lines intersect at one point. And that is when x is 10. When x is 10, that is 10 minutes of calls, all of the plans are $20. So if you knew you were going to make exactly 10 minutes of calls each month, there would be no reason to pick a plan. Any plan would be just as well, just as good for you. But what if you knew that you were making limited number of calls, less than 10 minutes? Well, you'll notice that if you do that, the horizontal line is on top. And the other three lines are below the horizontal line, and the line that provides the smallest cost, the smallest y value for any x less than 10, is the line with the greatest slope. And that is y equals 2x, because if you make less than 10 minutes of calls per month, the fact that there's no monthly charge allows you to have the lowest value. The numbers, by the way, you see on the screen, the x equals 15.11 and the y equals 30.21 are the x and y values for that point. You may say, well, no one is going to use 15.11 minutes. If they do, they're going to round it up to the next minute. But this particular calculator simply prints out numbers, and again, we're only looking at to see which line, which equation, which plan is best for us. So it appears that if we make less than 10 minutes of calls per month, we go with the $2 per minute, no monthly service charge. If we make more than 10 minutes per call, there's no question, looking at the four graphs, that to the right of the intersection point, the one that has the lowest cost is the horizontal line. And that is, of course, y equals 20, which means once we go past 10 minutes of calls in a month, paying $20 with no per unit charge means we're getting the best deal. So if this was your choices, once you knew how much you would make in calls, it would be very obvious from the equation, from the graph, which is the best plan. In the cell phone problem, all the points lined up to form the lines. In many real-world problems, where we use linear equations, we're dealing with data that is varied, and the line is an approximation of the points. That is, it represents the points, although the line doesn't go through all the points. Let's take a look at a situation where we have to approximate with a line to get a model. We're going to look at some data that involves the amount of fat in grams found in various types of pizza and the calories in each of those slices of pizza. Let's go to the TI-83. Here we have the pizza data displayed in the Cartesian plane. Each little plus sign represents a point. Each point is one type of pizza, the x-coordinate being the fat content in grams, the y-coordinate being the caloric content in calories. You'll notice that the points do not line up, but typically it appears that as fat increases, so do calories. We can write an equation, a linear equation, to approximate those points and to operate as a model so that we can talk about the relationship between fat and calories. I have selected two of the points, and one of the points represents a 4-gram fat pizza with 275 calories, and another was 19 grams of fat with 383 calories. I simply divided the change in y of the change in x and got a slope of 7.2. I estimated from the graph that the y-intercept would be about 250, and thus I have my equation y equals 7.2x, the slope of 7.2, plus 250, the y-intercept of 250. The 7.2, the slope, means that every time I add a gram of fat, on average, and the important on average, I expect to get an additional 7.2 calories. The on average is because, again, the line is an average of all the points. The points are not on the line. And now if we look at the points and the line, we can see that indeed it's relatively good in terms of kind of averaging out all the points. And by the way, that 250, the y-intercept, simply says that if we have a pizza sliced with no fat in it, we will still get 250 calories. Obviously, those calories come from carbohydrates in the crust and the sugar in the tomato sauce and any protein from the cheese and meat toppings. So we could also use this equation to predict. If we knew the number of grams of fat in a slice of pizza, we could use this equation to predict the calories. If we knew the calories, we could predict the grams of fat. Using a graphical representation of a linear function is quite useful. Another interesting set of data that I've looked at involves the relationship between national cigarette consumption and the mortality rate from coronary heart disease. This also can form a linear model to approximate points, each point representing a different country. The X would be the number of cigarettes smoked per adult per year in that country. The Y value would be the number of deaths per year from coronary heart disease per 100,000 population for people in the age range of 35 to 64. The age range was selected so if smoking had an effect, they would have a number of years of smoking, and beyond 64 was felt that there were other possibilities for causing heart attacks, and therefore that would be confusing for the data. When we chose 2 points, 1 point turned out for the United States to be 3,900 cigarettes per adult per year and a 257 CHD death rate. The other point had an X of 2,790 and a Y of 194. Using these 2 points, we obtained a slope of 0.057, which means that for every adult in the country, if every adult in the country smokes 1 more cigarette per year, that 0.057 people would die per 100,000 population from coronary heart disease. Now, 0.057 doesn't sound like a very big number, but again, think about how many hundreds of thousands of adult population there are in this country. The y-intercept obtained was 25. So now we have an equation. Y equals 0.057x plus 25. The 25 meaning that if no one smoked cigarettes, there was not a single cigarette smoked, we'd still have 25 people per 100,000 dying from coronary heart disease. We've seen the power of the linear equation. Next, in Lecture 8, we'll see the power of the quadratic and the cubic. See you then.